Okay, I want you to imagine a tool for a second. Let's call it a digital lightsaber.
Hmm.
And I'm not talking about, just a really sharp knife. I mean, a device that can cut through any lock, no matter how thick the steel, no matter how complicated the mechanism. You just point it, press a button, and the lock, it just melts away. Now imagine that lock isn't on a door. It's the encryption protecting your bank account,
Yeah.
your medical records, your private email.
It's a terrifying image, but honestly, that's the analogy we really need to grasp what's happening.
We're talking about the quantum arms race.
Yeah.
And look, I have to be the skeptic here for a moment. We've been hearing about quantum computing for, 20 years?
Mm-hmm.
It's always 5 years away,
Yeah.
Like fusion power or flying cars. But looking at the calendar, it's February 15, 2026. Does this date actually mean anything, or are we just buying into more hype?
That skepticism is fair. It really is. But things have shifted. We've moved from, let's say, theoretical physics to engineering problems.
Okay, and that's a big deal.
That is a massive difference. We are rapidly approaching what the industry is calling Y2Q, or a Q day.
Q day.
Yeah, the hypothetical date when a quantum computer becomes powerful enough to break the encryption standards that, hold the entire internet together.
So the mission for this deep dive is to figure out if we're actually safe. We've got a stack of research here. Everything from the mechanics of Shor's algorithm, which I guess is our lightsaber,
That's the one?
to some brand new papers that literally just dropped this month. We're going to unpack the two big villains, Shor's and Grover's algorithms,
Yeah.
and explain why your data might already be compromised, even if that computer doesn't exist yet.
And we also have a major curveball to talk about. There's a preprint paper from just a couple of weeks ago, February 3rd, 2026, by a researcher named Jose Israel Nadal Vidal. It suggests that one of these huge threats might just be a Pater Tiber.
Okay, I want to get to that twist, but we have to eat our vegetables first. Let's talk about the big bad, the lightsaber, Shor's algorithm. Peter Shor came up with this way back in 1994. Why is everyone so afraid of a math equation from the 90s?
To understand why Shor's is a world ender for privacy, you have to understand how we secure the internet today. We use public key cryptography, mostly RSA, and the security of RSA relies on one very specific math problem, integer factorization.
Which is just unmultiplying numbers.
Basically, yeah.
Yeah.
It is incredibly easy to take two huge prime numbers and multiply them together to get a result. A pocket calculator can do it. But if I give you that result and ask, okay, which two numbers did I multiply to get this? That is incredibly hard.
The sources mentioned that to factor one of these big numbers using a classical computer like the one on my desk, it would take something like 2,000 years of processor time.
That's the bottleneck. Classical computers have to try dividing the number by 3, then 5, then 7. It's just trial and error. But a quantum computer using Shor's algorithm can theoretically do this in what's called polynomial time.
Okay, stop there. Polynomial time.
Yeah.
I see that phrase in every computer science paper. What does it actually mean for us regular people?
Think of it in terms of scaling. In the classical world, every time you add a digit to the number you want to factor, the time it takes to break, it explodes. It grows exponentially. But polynomial time means the difficulty grows much, much slower. It turns a problem that takes 1 billion years into one that might take a few hours.
So it's not just a faster computer, it's a shortcut through the math itself.
It is a complete shortcut. And this is where it gets really weird. I watched that minute physics breakdown you sent, and it highlights something crucial. Shor's algorithm doesn't just guess factors faster. It turns the whole problem into a frequency analysis problem.
Frequency analysis, like tuning a radio.
That's a great way to put it. In math, there's this thing called modular exponentiation. If you take a number and keep multiplying it by itself, but you use clock arithmetic, the remainders eventually start to repeat. They form a pattern, a loop.
Okay, let me try to visualize this. So if I have a clock with, say, 15 hours on it and I just keep adding hours, eventually I come back to where I started. There's a cycle.
Yes. And the length of that cycle, the period, that's the key. If you can find the period of that function, a little bit of classical algebra lets you derive the factors of the original number.
Right.
The problem is, for big numbers, that period is gargantuan. A classical computer has to check one point at a time to find the pattern. It would take forever.
But a quantum computer doesn't check one at a time. It cheats.
It uses superposition. It can essentially test all possible integers in the function simultaneously.
I think this is where people get lost.
Yeah.
I mean, it inputs everything at once, but doesn't it just give you 1 billion answers, and most of them are garbage?
It does, absolutely. And this is the magic trick. You have a state that contains all the right answers and all the wrong answers mixed together. Then you apply something called the quantum Fourier transform. Think of it like noise-canceling headphones.
Destructive interference.
Exactly. The quantum Fourier transform manages these waves of probability. It makes the wrong periods destructively interfere. They just cancel each other out to zero. But the right period, the true cycle, it constructively interferes. It gets amplified.
So when you measure the computer, the only answer left standing is the right one.
Well, in the quantum world, nothing is ever quite that perfect. You get the right answer or a number close enough to derive it about 37.5% of the time.
That sounds low. Less than a coin flip.
It does sound low, but remember, computers are fast. If you run the algorithm, say, 10 times, the probability of not finding the answer becomes microscopic. You are effectively guaranteed to break the code.
That is just wild. It's using the physics of the universe to solve a math problem. But let's ground this for a second. We've been hearing it's coming forever. Where is the hardware in 2026? Are we still, factoring the number 15?
We've moved past 15, thankfully, but no, we aren't cracking bank vaults yet. However, the roadmap has accelerated. There was a pivotal study recently that suggested if you had 20 million noisy qubits.
Noisy meaning imperfect.
Right, imperfect qubits. You could break a 2048-bit RSA key, the standard lock on the internet, in about 8 hours.
8 hours, one work shift to unlock everything.
And that brings us to the part that actually scares me. You asked earlier, if the computer isn't ready yet, why are we panicking today?
Yeah, if the burglar alarm doesn't work yet, why am I worried about the burglar?
Because the burglar is already in your house stealing the safe. They just can't open it yet. This is Harvest Now, Decrypt Later, or HNDL.
Harvest now, decrypt later. It sounds like a spy movie trope.
It's very real. Intelligence agencies, nation-states, they are scraping encrypted traffic off the internet right now. They're storing it in massive data centers. They know they can't read it today because it's locked with RSA, but they're just hoarding it, waiting for Q-Day.
So this all comes down to data relevance longevity. That was a term in the notes.
Exactly. Think about it. If they harvest your credit card number today and decrypt it in 10 years, who cares? That card expired back in 2029.
But if they harvest my genome...
Bingo. Or the blueprints for a power plant. Or diplomatic cables between allies, or your social security number, that data doesn't expire. If you send that data today using standard encryption, you have to assume it is already compromised. You are broadcasting your secrets to the future.
That's a heavy realization. We're basically betting that the future won't be able to read our mail, and we're losing that bet.
We are, which is why the transition to new encryption is so urgent. But before we get to the solution, we have to talk about the second villain. We've covered Shor's algorithm, the lightsaber. Now let's talk about Grover's algorithm.
Right, Grover's. This one's different. Shor's goes after the keys. Grover's is more of a brute force thing, right? It attacks symmetric encryption, like AES, which is what we use to actually lock up the files themselves.
Correct. Grover's isn't about finding a hidden period in the math, it's a search booster. Imagine you have a phone book with 1 million numbers but no names, and you need to find who owns a specific number. Classically, you have to check every single entry until you get lucky.
Which, for a 128-bit key, would take longer than the age of the universe.
Right. But Grover's algorithm gives you a quadratic speedup. It's like turning a search of n items into a search of the square root of n steps. Practically, this means it cuts the security in half. So if you have a lock with 128-bit security, Grover's makes it feel like it only has 64-bit security.
And 64-bit is something a generic laptop could crack.
Easily. So for the last decade, the advice from every security expert has been the same. Just double the key size. If you use AES 128, switch to AES 256. You double the key, Grover's cuts it in half, and you're back to 128 bits of security. Problem solved.
But this is where we get to that plot twist. The 2026 surprise, the Vidal paper.
Yes, the Vidal paper. This is fascinating because it challenges the physics of the attack. Vidal looked at what it would actually take to run Grover's algorithm on real hardware.
Because quantum computers are noisy, right? They aren't perfect logic machines. They're dealing with subatomic particles that jitter all over the place.
They are incredibly fragile. Now, Grover's algorithm relies on something called an oracle. In computer science, an oracle is basically a function that checks if you've found the right answer. It marks the winner.
So the oracle checks the phone book entry and just says yes or no.
Right. But here's the catch. Grover's algorithm works by something called amplitude amplification. It takes the probability of the correct answer and it slowly rotates the vector toward it. It has to do this over and over again, thousands or millions of times.
Is building a tower of probabilities bit by bit.
Exactly. But what Vidal found is that if the oracle is even slightly imperfect, if it glitches just once due to noise, it doesn't just stall the progress, it reverses it. It scatters all the probability you've built up.
So if the checker messes up even once, the whole calculation just collapses.
The math is brutal. For a tiny search, the oracle has to fail less than once every 800,000 iterations. For cryptographic sizes like breaking AES, the reliability you'd need is, well, it's effectively impossible with any near-future hardware. You would need a quantum computer so perfect it might never exist.
Wait, so this is good news.
It is massive good news. It suggests that Grover's algorithm might be a theoretical boogeyman that can't actually walk around in the real world.
So AES 128 might actually be safe.
It might be. We shouldn't get complacent, of course, but the brute force threat is looking much weaker than we thought. Shor's algorithm, however...
Shor's is still the lightsaber.
Shor's is still coming for our public keys. The noise doesn't kill Shor's the same way it kills Grover's.
Okay, so the lightsaber is real, but the brute force hammer might be broken. We still need a shield for the lightsaber. Which brings us to post-quantum cryptography, or PQC.
The shield. NIST, the National Institute of Standards and Technology, has been running a competition for years to find new kinds of math that quantum computers can't solve.
And we finally have winners. Back in August 2024, they released the first finalized standards, FIPS 203, 204, and 205.
A historic moment. But notice they released different tools for different jobs. FIPS 203 is based on Crystal's Kyber. That's for encryption, for locking the box. Then for digital signatures, proving who you are, we have dilithium, Falcon, and CNCSCTS.
Why do you need different math for locking a box versus signing a document?
It's all about the structure of the attack. But the important thing is that most of these, Kyber and dilithium, they rely on something called lattice-based cryptography.
Lattices. I tried reading up on this and my eyes just glazed over. It's a grid, right?
Imagine a grid. In 2 dimensions, like on graph paper, it's easy to find a point. Now imagine a grid in 500 dimensions. This is a hyperdimensional lattice. And the hard problem they use is called learning with errors.
Okay, learning with errors. Break that down for me.
Imagine I have a secret point on this 500-dimensional grid. I give you the coordinates, but before I hand them to you, I add a little bit of random noise to each number. I kick the point slightly off the intersection.
So I get a fuzzy map.
A very fuzzy map. And your job is to find my original perfect point. For a classical computer that holds the private key, the noise is easy to subtract. But for a quantum computer trying to solve it from the outside, it's a nightmare. The period finding trick from Shor's algorithm just doesn't work here. There is no period to find, it's just unstructured noise.
It's like trying to listen to a specific conversation at a really loud cocktail party. If you know the person's voice, the key, you can filter it out. If you don't, it's just static.
That's a perfect way to put it. The quantum computer just hears static.
Now, looking at our timeline, there was another update just last year, March 2025. NIST added another algorithm, HQC. What, did Kyber break or something?
No, Kyber's fine. This is about risk management. Kyber and dilithium are both lattice-based. If, and this is a big if, heaven forbid some mathematician next year discovers a fundamental flaw in lattice math, we lose everything. Both standards would fall at the same time.
Ah, so HQC is the backup plan.
It's the diversity plan. HQC is code-based cryptography. It uses completely different math involving error-correcting codes. So if lattices collapse, HQC is still standing.
It's like diversifying your stock portfolio. Don't put all your security eggs in one mathematical basket.
Precisely. And that leads to how companies are actually deploying this stuff. They aren't just ripping out RSA and plugging in Kyber. That would be reckless.
Because Kyber is new, and new things have bugs.
The standard strategy now is hybrid encryption. It's a real belt and suspenders approach. You encrypt your data with the old trusted RSA or elliptic curve, and you also wrap it in the new post-quantum algorithm.
So if the quantum computer comes along and breaks the RSA belt...
The Kyber suspenders are still holding your pants up.
And what if it turns out Kyber has some classical bug nobody found yet?
The RSA belt keeps you safe. It's really the only responsible way to transition. Google and Cloudflare have been doing this for a while now.
The sources also mentioned crypto agility. That definitely sounds like a buzzword.
It is, but it's a necessary one. It just means building your systems so you can swap out the encryption algorithm easily. In the past, developers would hard code, use RSA 2048 deep in the software. You'd have to rewrite the whole app to change it.
which is a nightmare if a vulnerability is found on a Tuesday and you need to patch it by Wednesday.
Exactly.
Yeah.
Crypto-agility means the system just says, use whatever the current standard is. If the standard changes, you update a config file, not the code. We can't just set it and forget it anymore.
So let's try to synthesize all this. We've got Shor's algorithm, the Lightsaber, that is definitely going to break our current public key encryption. We've got HNDL, meaning our long-term secrets are being stolen right now to be opened later.
Right. But we also have this 2026 insight that Grover's algorithm, the brute force threat, might be hamstrung by hardware noise, which is a win for defenders. And we have the new NIST shields, Kyber, Dilithium, HQC, ready to be deployed.
It really feels like a very high-stakes race.
Okay.
Attackers building the sword, defenders building the shield.
It is. And if I can leave you with one final thought that keeps me up at night.
Oh, great. Just what I needed. Go ahead.
We talk a lot about the technology, but think about the geopolitics. We are racing to deploy these shields. But what if a nation state, let's say a global superpower, achieves a working, scalable quantum computer in secret, 6 months before the rest of the world finishes migrating to these new standards?
You're talking about a window of transparency.
Window of total visibility. For that 6-month window, the world is made of glass to them. Every diplomatic cable, every bank transaction, every military order sent over the internet would be readable, and no one would even know it was happening.
They could read the opponent's playbook in real time.
That window of time wouldn't just be a security breach. It could reshape the global order before we even realize the window is open.
Well, on that absolute horror movie note, I think the actionable advice here is pretty clear. Go check your organization's data policy.
Do you have a data relevance longevity policy? If you're saving secrets today that need to be secret in 2035, you better be encrypting them with post-quantum standards now.
The future's already here, and it's listening. We just need to make sure it can't understand what we're saying. Thanks for deep diving with us.
My pleasure, as always.